Zhongmei Wei come from Singapore. Also the co-chair with the Feng Chen and the Kaiser Lin. The paper title is Large LDPC Code for Big Data Storage. Let's welcome Zhongmei Wei.
Okay, so my topic is large LDPC codes for big data storage. Okay, let's look at the challenges of big data storage and analytics. As we all know, the data volume is extremely huge for big data, and the volume is continuing to explode due to different applications like social media, or even the most recent IoT applications. And for the traditional technology to provide reliability, because we store the data in the computer, and the computer might be unavailable or might be down due to hardware failure. That's why normally we will have some technologies to introduce redundancy to provide certain level of reliability. So the most traditional way is using replication. So that means you have 1G data, you make multiple copies. In case one copy of data is lost, then we can retrieve from the other copy. But for this technology, obviously, it needs a huge amount of space to store just maybe 1G data. For example, for Hadoop platform, the default replication rate is 3. So there will be 200% spatial waste, not so-called waste. Okay, you reduce the total applicable amount of your space. So that's why it demands spatial efficient technology to provide the same level of reliability. And another challenge faced by the big data storage or analytics is because we have a huge amount of data, so the platform or the cluster, in order to process this amount of data, is very big. Let's look at some examples. For example, the Facebook's production cluster, there are more than 3,000 nodes. And 30 terabyte logical data storage. And Google has tens of storage cells. Each cell contains from 1,000 to 7,000 nodes. So that will lead to a higher chance of nodes failure. And there are certain reports reporting that it is quite common to have 20 node failure per day. So look at this situation, we understand that whatever technology to provide reliability, it has to be able to provide very high reliability to tolerate the possibility that more nodes will be failed or unavailable. So that's why people are starting looking at another way of adding redundancy. So previously we have the simple replication-based method, and then we have this erasure-based framework. So how the erasure-based framework works is we have a number of data chunks, and then you divide it into chunks. In order to add redundancy, we don't replicate data, but on the other hand, we do some so-called encoding to generate some parity chunks. And then we store both the data chunk and parity chunks. So in the event of failure, for example, we have 10 chunks, right? 9 chunks, and then we distribute it into 9 nodes. For example, if node 4 is failed, we gather a few parity chunks and data chunks to recover the data, the lost data. So in this way, we can reduce the space required to achieve the same reliability compared with the traditional replication-based method. Let's look at some of the existing current technologies under this erasure-based framework. So one of the golden standards is called Reed-Solomon code. This code actually already been widely used in storage For example, if you have heard of a read disk, they're actually using, if it is read 6, it is actually using Reed-Solomon code. But for this type of code, it provides the optimum trade-off between the reliability and the spatial space required. But because it uses Galois field operation, the computation cost is very high. And when we are talking about distributed storage, it needs higher repair traffic. So for this code configuration, we need n times repair traffic. That means if you, let's say you lost 1 G data, you need to gather n G data in order to recover this 1 G data. And this will pose a big challenge for the cluster because your cluster needs to do other things. And now your repairing traffic will occupy a large portion of your network traffic, which is not desired. That's why a few big companies are trying to investigate new codes to solve these problems. So for example, there are local repairable codes from Facebook and Microsoft. Both of the codes are based on RS code. They do some modifications. They introduce local parity chunks so that they reduce the repair traffic for single erasure. Okay, and besides these Reed-Solomon codes and the variables, there's another category of erasure code called low-density parity check codes. For these codes, compared with Reed-Solomon, which use Galois field operation, LDPC code only use XOR operation. We all know XOR operation is much faster than Galois field if we implement it into on the computer. And also, our previous work already showed that the repair traffic is determined by the row weightage of H. If you look at what this code name is low density. Low density means the weightage of your parity matrix is very low. So that gives you a very low repair traffic. This is advantage for this code. And next thing, that's why for our paper, we're trying to tackle some of the challenges. For example, for the work based on RS code and also some of the network codes, they have the following disadvantages. For example, their encoding complexity, that means the way how they apply to add the redundancy, is the complexity is high. And it is, for those variances, it is even higher than RS code. And also, they have limited reliability because if they want to increase the reliability, they need to increase the code size. And actually, the complexity will increase quadratically. So that means they cannot use a very big code because the complexity cannot be handled by the computer. And then if we look at the LDPC related work, currently there are still no detailed analysis on repair traffic for multiple erasures. So multiple erasures means multiple nodes may be unavailable or fail due to hardware malfunction. So that's why the objective of our paper is to explore the large size LDPC code to provide a higher reliability, and at the same time we want to investigate the repair traffic for single and multiple erasures. So we start from the simple one, which is a single erasure, because for any erasure code encoded data, you need to satisfy this equation. So in the event that the first chunk corresponding to the first column, if the first chunk is erased or is lost, unavailable, we can use this equation to recover. So that means in order to recover the first chunk, we need the second, 4th, 8th, 11th, 17th, and the 9th and 20th chunks. Gather these few chunks in order to repair the one chunk. If we look at multiple erasures, this is an example. For example, our first, second, and third chunks are lost. Then we need to use this formula to recover the lost chunks. So if you look at this one, we can check, because we already know for each single erasure how many traffic we know, that is determined by the row weightage of the, this is the parity check matrix. So we can get a conclusion that we can look at this table. If the single erasure needs this traffic, J represents the row weightage. For the P number of erasures, the total traffic will definitely be smaller than P times the row weightage of the parity check matrix. So that means if let's say we can design codes with very low row weightage, we can at the same time reduce the repair traffic for both single erasures and multiple erasures. And we've done some. So this figure shows you where the codes are, where are those selected LDPC codes compared with Reed-Solomon code and the local repairable codes. So we can see we tried 4 configurations of LDPC code, even including very large ones. So if you look at here, we have 240. That means original data is divided into 240 chunks, adding 120 chunks as the parity chunks. So we can achieve a very high reliability with only 1.5 redundancy rate. So only store half of the original size, but we can tolerate up to 24 nodes failure. And if we look at the repair traffic, this table shows the single erasure. That means one node is failed. These are the repair traffic we need for different LDPC configurations. So we can choose configurations which is as low as 2 times of the original data. And then this table shows the 2 erasure. That means 2 nodes are unavailable, and this represents the 3 unavailable. So most importantly, if you look at here, 2x, that means 2 times of the repair traffic will be reduced to 1.95 times repair traffic per chunk for 2 erasures. For 3 erasures, this one is even lower. So we can see the LDPC code can also ask low repair traffic, not only for single erasure. For multiple erasure, you can see the trend. Actually, the repair traffic per chunk is reduced, even with the increase of the number of erasures. This one is in contrast to the Reed-Solomon code, where only for single erasure there are technologies to reduce the repair traffic, but for multiple erasures, they still need to gather all the data chunks in order to recover the multiple erasures. And furthermore, we have done some simulations in Hadoop clusters. So here is a summarization of the decoding latency and HDFS bytes read. So this will represent the repair traffic. So we can see that the decoding latency can be largely reduced if we compare the LDPC code, all the configurations of LDPC code, and the RS code and its variations. This is because for RS code decoding, you also need to use the gallows field operations, which demands more computing power compared with simple XOR operations. And for HDFS bytes read, we can see also for certain configurations we can achieve reductions in terms of traffic. The reason why these fields are still higher than this one is because we are using a very high, very large size of code. And for that large size of code, we can achieve higher reliability, but the disadvantage is the repair traffic is higher than the RS code. But we are still investigating the new way of designing LDPC code to achieve even lower repair traffic, even compared with the small RS code. So this comes to the last slide of my presentation. So we have finished the theoretical analysis of repair traffic for both single and multiple erasures. And LDPC code has its own unique advantages of improving reliability without largely increasing the repair traffic and computational cost. And we can see our results show significant improvements in terms of the decoding latency. And in the future, we will be further exploring ways to construct LDPC code based on the criteria we have designed to provide high efficient methodologies to reduce the repair traffic. So that's the end of my presentation. So any questions?
Any question for the first paper? No. Just a question. I saw your experimental environment is HP workstation. That's four workstation, right? And each run about 12 VM virtual machines. So the virtual machine number will influence your algorithm or not, or like the physical infrastructure will
for each virtual machine, the reason why we use a virtual machine because we can simulate a bigger cluster. Because if we don't use virtual machine, then we have to buy 48 nodes, and the node is very expensive. I think it's all this setup, the hardware is around 70,000 Sing$. So I don't know how you may have to multiply 20 or 24 into Taiwan dollars. But the most likely, I think, should be fine. Why? Because for each virtual machine, we have allocated 2G memory. So roughly, we are only running a small, we are only running Linux CentOS OS, so 2G should be enough. So still, the result shouldn't be too much to our average. Okay, bye.
I have a quick question. Good work, by the way.
Thanks.
So, how do you pick up H matrix? Depending on the size of the cluster and
Okay, yeah, good.
Do
Also
you
good
have
question.
all H matrix for all possible sizes, or you calculate online?
We believe that there's no one optimal code configuration for all the cluster configurations. So that's why we actually are developing a library of LDPC codes, and different size will cater for different size of cluster. So if let's say you have we have the configurations like a few hundred, right? So that means at least the cluster size has to be a big cluster, so maybe 1,000 or a few hundred. Otherwise, it's not meaningful to apply this such a big size of LDPC code. So there's no one size for all, but we do have a different size for different size of clusters. And in terms of the designing of the codes, we already came out with some of the way to construct the codes, because we can see the repair traffic is determined by the row weightage. So we want to find codes with low weightage or targeted low weightage. For example, you want 5 times of the repair traffic, 5 times of the original data. Then we can have a way to come out with a code with 5 times repair traffic and with the corresponding block size and code size. So it's adjustable, in another word.
Thank you. I have a lot of questions. We'll ask offline.
Okay,
Okay,
sure.
yeah.
Thank you.
Okay, let's give you a big hand and thanks for our first one paper. It's a John Wei. Let's